So what do we mean by potential energy? Let's do the potential energy due to gravity. We know gravity is a conservative force, so we know that we can define a potential energy due to gravity. And we say, okay, so let's say that we go outside and we get an Amazon package, and we want to bring the Amazon package in. So we got to lift it up from the ground. Presumably it was left on the ground. And as always, we've got an object with mass m, and we lift it up a height h. And we know that the work done by gravity, in order when we lifted it up, was minus mgh. And so what this tells us is that we have changed the potential energy. If the work done by gravity is minus mgh, and that's minus the change in potential energy, therefore we have changed the potential energy of the Amazon package by mgh. We have increased the potential energy by mgh. And we know we've increased the potential energy because if I drop it, it's got velocity. You don't want to drop it, you don't want to break what's in it until you know what's in it, at least. It's that simple, right? So we've now got to change the potential energy. And we can use that in any in any problem when you're asked to solve using energy conservation. So for example, I can ask the age-old question. If I drop a box of mass m from a height of h, how fast is it going when it hits the ground? We discussed that problem in kinematics. We discussed that problem in Newton's second law. We discussed that problem in the work energy theorem. Now let's look at it from an energy conservation point of view. Well, if I gave it potential energy on the way up, delta PE is mgh. When it's on its way down, delta P must be minus mgh, right? If I've increased the potential energy on the way up, it's going to decrease back down on the way down. So on the way down, the change in potential is minus mgh. So first of all, delta PE is equal to minus mgh when it falls from up to down. And we know that, or you know that because you know the work done by gravity was plus mgh, and the change of potential energy is the opposite of that, minus mgh. Okay, so and so the delta Ke is unknown, but it's 1/2 mv final squared minus 1/2 mv initial squared, and delta Ke plus delta Pe is equal to 0. That's energy conservation if there are no non-conservative forces, which there aren't because we didn't say there was going to be friction. So therefore, we have 1/2 mv final squared minus 1/2 mv initial squared minus mgh is equal to 0. That's what energy conservation tells us. Hopefully you can see that understanding the negative signs is really important here because like we're adding these energies, but potential energy is negative. We're subtracting these kinetic energies, right? So that's where these minus signs come from. You should just understand that. Okay, so now we're dropping it from rest. That was implied. We're dropping it from rest. So this is 0. So therefore, we can solve for V final. V final equals the square root of 2gh. That's what you get when you solve. Oh, we had figured that out a million times before. That's the velocity when you drop something when it gets to the ground. But that's from an energy conservation point of view. Energy conservation. Delta Ke plus delta Pe is 0, or E, delta E is equal to 0 is the same thing. Okay. One thing I want to talk about before we do more examples is this concept of potential energy due to gravity. So far, all we've got is change in potential energy due to gravity. But what is the potential energy at a point? In other words, what is the potential energy right here? PE, I don't know, if we lifted it up, PE final, versus what is the potential energy right here? PE initial, or vice versa. But what is the potential energy at a point? All we've talked about is change in potential energy. Let's look at this in terms of our Amazon box, which we're lifting up from the ground. And we're either going to put it on a table, a height h1 above the ground, or maybe even a height h2 above the table if we're going to carry it in. And let's just also just say that total height, h1 plus h2, is h3. And let's also define my position at the ground, h0. So really, my position at the ground is h0. This is my At the table, my position is H1. At the top of at the highest I lift it, my position is H3. Or, okay. The question I want to ask is, what is the potential energy due to gravity, so PE sub G, versus the change in potential energy due to gravity, which is what we've been looking at so far. So we haven't talked about the potential energy at a point. In other words, what is the potential energy due to gravity at H0? What is the potential energy due to gravity at H1 above the ground? What is the potential due to gravity at H3 above the ground, or H2 above the table? What is it at those points, rather than the change in potential energy? So first we know that work equals minus the change in potential energy. So we know the changes, because we know, for example, the work, and again, this is in general, but for gravity, the work done by gravity from the ground to the table, so let's say from 0 to 1, is equal to minus mgh1, because gravity is trying to pull it back down, so it's a minus. It's minus mgh1. The work done by gravity from 0 to 2 is equal to, just not writing down all the letters, is equal to minus mgh3. Don't get confused, because I'm calling H2 the height above the table, and I'm again lifting it from the ground, so 0 to 1 to 2, and that's just, we could have said, right, that's minus mg H1 plus H2. Maybe that would have made more sense. Okay, that's the work done by gravity. And we could say the work done by gravity, let's say I put it on the table, and then I lifted it up from the table, so the work done by gravity from 1 to 2, the work done by gravity, I'm just not writing the words, oh, why not? Work done by gravity from 1 to 2, is equal to, from 1 to 2, I've lifted it through a height h2, so it's minus mgh2. So we know the work done by gravity, and so we know, therefore, that is minus the change of potential energy going from 0 to 1. This is minus the change in potential energy going from 0 to 2. And this is minus the change in potential energy due to gravity. I didn't write, again, I'm not saying that explicitly, but this is all due to gravity, minus the change in potential energy going from 1 to 2. Therefore, I hope it becomes pretty obvious that if I go ahead and get rid of my minus signs here, or cancel my minus signs, therefore the change in potential energy from 0 to 1 is equal to mgh1. And the change in potential energy going from 0 to 2, and I didn't leave myself any space, is mgh3, going from the ground to the top height, or mgh1 plus h2. And therefore, the change in potential energy going from 1 to 2 due to gravity is equal to mgh2. And I'm still asking the question, but what is the potential energy at h3? What is the potential energy at h1? What is the potential energy at the ground, at h0? And it might be pretty obvious, oh, we really just need to define the potential energy at a point as mgh, due to gravity, as mgh. But since we're defining the potential energy at a point, h, we're measuring h from where? Different than measuring the work. When we measure the work, we automatically say if we're measuring the work, we have to have moved from somewhere. If we're measuring the work, we have to move from one place to another place. If we measure the work, we have to move from one place to another place. If we're talking about the potential energy at a point, we're not saying we ever moved from anywhere. So where are we measuring h from? And this is what the beauty of the potential energy is. It's wherever you want to measure it from. It's wherever it's convenient. So in this case, you might say, well, obviously we're measuring from the floor. So by saying we're measuring from the floor, so let's say, for example, if we are measuring from the floor, what we're saying is that at the floor, we're saying h is 0, and we're saying PE at the floor is 0. Therefore, we can say that at h1, h is h1, and PE is equal to mgh1. And therefore, we can say that at h3, the potential energy at position 3 due to gravity is mgh3. And you say, well, that was obvious. Why do we have to go through all that? Well, let me show you why. Let's go ahead and make sure that the delta PEs are what are defined. Make sure they make sense in this case where we've defined h equals 0 at the floor. The change in potential energy from 0 to 1 is indeed mgh1 minus 0. It's mgh1. The change in potential energy from 0 to 2, it's going from here to here, is mgh3 minus 0. mgh3 minus 0. It's mgh3. Okay, good. The change in potential energy going from 1 to 2, going from here to here, is mgh3 minus mgh1, right? It's potential energy final, right, at 3, minus potential energy initial at 2, mgh3 minus mgh1, which is indeed 3 minus h3 minus h1 is h2. That's what we get. Okay, so it all makes sense if we define potential energy as mgh, where h is 0 at the floor. But what if we say h is 0 somewhere else? I'm going to go ahead and erase a lot of this and then say what happens if h is 0 somewhere else. Say, oh, well, we're lifting it up from the table, so let's just define that as my potential energy of 0. So let's call the potential energy here equal to 0. Well, if I lift it up, if I define that as my 0, and then I lift it up to here, therefore, at this point, the potential energy, which is mgh, where we're measuring h from 0, it's going to be mgh2, right? Because I'm lifting the box up from here to here. So it's mgh2 because this is my 0. And that means that if I go down, remember potential energy has to go up as we go up. So if I go down, the potential energy here is minus mgh1 because potential energy is measuring h upwards. We didn't say the word, but we implied we're measuring h upwards from somewhere. So if we go down, the potential energy has to be reduced. So if we go down, the potential energy has to be reduced. That's why we've got a minus mgh1. Okay, so we say if we define potential energy this way, and we define our h equals 0 at the table height, then the potential energies are as follows. And all that matters is that these must still be true, because this is all defined from this. So, what is, given the new potential energies, what is delta PE from 0 to 1? It's PE1 minus PE0, which is PE1, which is 0, minus PE0, which is mgh1, which is minus mgh1. So it's still the change in potential energy going from 0 to 1. Obviously, you caught my minus sign error because it's minus PE1 minus PE0 is 0 minus, and now the potential energy at 0 is negative. So this is minus mgh1. And so the change in potential energy is plus mgh1. Okay, that matches, that works. And the potential energy from 2 is PE2 minus PE0. We got to fill in PE2, mgh2, and PE0 is minus mgh1. So minus a minus mgh1. So that gives us mgh2 plus h1. h2 plus h1, which is indeed the potential energy going from 0 to 2, right? It's mgh1 plus mgh2 plus h1 is mgh3. Right? So that's mgh3, and so that still works. And then you can do the other one on your own, right? Going from 1 to 2. Going from 1 to 2, you can show that if I go from here to here with h equals 0 here, with potential energy equals 0 here, then the change in potential energy is mgh2. So here's the point. Potential energy due to gravity is going to be defined as mgh, where h is measured from a position you define as h equals 0 And at that point, the potential energy equals 0. So you might measure the potential energy from the ground and say the potential energy on the ground is 0. So as I lift it up from the ground, I now give it additional potential energy of mgh. Or you might measure the potential energy from the table. Say that on the table, the potential energy is 0. And I'm going to lift it up and give it potential energy mgh, where h is measured from the table. You define your 0. And typically, the easiest thing to do in a problem is to define h equals 0 at the lowest point. So if we're only talking about moving things from the table, you can define h equals 0 at the table. If you're talking about moving things from the table to the floor, then you might define h equals 0 at the floor, etc. Generally going to be true, because the work done by conservative force is defined as minus the change in potential energy. It doesn't define the potential energy at a point. Whenever you define a potential energy due to anything, gravity, mgh, or let's say a spring, you need to define 0. What we will see, or what we can easily see, is that the potential energy due to a mass on a spring is equal to 1/2 kx squared. But where are we measuring x from? Again, we're measuring x from a defined 0, and it's always easiest for a mass on a spring, for example, to define your 0 as the point at which the mass doesn't want to move, right, at its equilibrium point. So in that case, you're actually defining the potential energy equal to 0 at its equilibrium point, not at one end or the other end of the mass's movement. And this is going to always be true when you define potential energies, is you've got to define the 0. Or there may be an obvious place that we're going to define the 0, but it is an arbitrary definition. Okay, there you go.